So can everybody see OneNote?
Yeah.
Okay, so thank you. So yes, I will put out some example stuff to help you study. So I haven't been able to get that all put together yet, but you'll have, some days to work on it, and then I'll post a solution probably by the weekend since the final is on Monday. And what you can expect with this, it'll be like an outline plus some practice problems for magnetism. And the more recent stuff, just so you have kind of some sense of what you're responsible for, to give you a little more confidence and certainty as to what to look for, expect on the final. Let's see. The final itself is on Monday. Actually, let me pull up the exact date just to confirm it here. One moment. So 2 to 4. It's going to be a little bit of a weird situation because it's in 2 different rooms. So, but hey, good on you. You got an afternoon time. My students last quarter had their final at 8 a.m. Despite never having had class at that time. Their final was at that time, which was kind of a brutal draw, I felt.
Yeah, that was terrible. Disgusting. Terrible. For what?
It wasn't you. It was the other.
I don't care.
Stuff.
It's just the thought. Ours was like 9.
Yeah, so consider yourselves already lucky that you've got a nice afternoon time. And it is on, so Monday, that would be, let's see, the 22nd. And it's in CC 210 and CC 244. This is just because of the room, room capacity issues. So I'll go verify where that is exactly and shoot you guys an email, to give you a little bit of guidance. But I would recommend, since you've likely had classes in these rooms, but if you're, totally unfamiliar with that, you might want to check it out beforehand just to make sure you know where to go, or just give yourself a lot of time before it actually starts. In any case, that's when the final is, and that we'll have a study guide that's coming. Okay. Any other questions about that stuff? So the next thing is our completion quiz here. Let me try and paste it in. Okay, so with regards to the completion quiz, like I said, thanks again for looking at this. It helps me to understand how you're doing with stuff, and it also messages to you a little bit what you're responsible for. So the first question, people generally did really good on this one. I think since we've been messing with this in lab and stuff, you seem to be, most everyone has a pretty good idea of how to approach this. So the first thing it asks you about the force. So once you're in this magnetic field, you would just apply, your right-hand rule, QVB, point your fingers in V, and then curl them into the page, and you would find that your thumb is pointing in this direction. That would be the direction of the force. Now, if the charge were negative, it would be in the opposite direction, be going down. The next part is asking, find the radius for some combination. So instead of looking at an electron or something, we're looking at carbon-12, and it gives us the mass, and it gives us the magnetic field, and it gives us the speed. So I think it's useful. You can just rederive this rather than trying to remember some expression or something, you know that the sum of the forces is going to be equal to the mass times the acceleration. In this case, we're talking about something that's going in a circle. So this will be a radial situation. The force is going to be QV cross B. And we know that the radial acceleration, the centripetal acceleration, we can express its magnitude as v squared over r. And then we also know that this cross product, since v and b are perpendicular in this kind of situation, this just becomes qvb equals mv squared over r. So this one factor of v would cancel out, and you could solve this then for r. R will just be m v over qb. And then we could put in our numbers. So the mass is going to be 12 AMU, where an AMU is basically essentially the mass of a proton. So, and then the velocity would be 0.01 times the speed of light, 3 times 10 to the 8th. And then the charge, well, it has a charge of +1, the charge of the electron, because it's just been ionized once. So you know that's 1.602 times 10 to the minus 19. And then the magnetic field was 2.5 Tesla. So you put those numbers in and turn the crank, and you would find that this radius would be 15 centimeters. And that looked like most folks were on the right track with that. So that was part B. And then part C was asking, what electric field magnitude would be required to keep this thing going in a straight line. And you can think of this as when you look at the full Lorentz force, what this is telling us is that the electric field and the magnetic field have to cancel, because you know that this has to be equal to 0 if this is moving in a straight line. In other words, the sum of the forces is 0. And so how that can happen is if the E field is canceling out, or the force due to the electric field is canceling the force due to the magnetic field. So in other words, another way to think of this would be that the sign of this would have to be, one of these would have to be negative relative to the other one. So we know that E has to equal V cross B. We also know that these are perpendicular to each other, so this just becomes VB. So if you know the velocity, you can solve this. Well, this is already solved for the electric field, which is what we're looking for. So this would just be 0.01 C times the B field. And you would find that this gives you 7.5 times 10 to the 6th. And it looked like folks were pretty good on that as well. So that's the first question. Did anybody have any questions about that one?
I had a question for B. So the charge was just charge of an electron.
Yeah, because it's been ionized once. So you can think of it, if it was neutral, it would have 12 electrons because it's carbon. Or wait, no, it would have 6 because whatever the atomic number of carbon is, right? Let's see here. Yeah, so it would normally have 6, but you've lost 1 electron. So it would have 5 electrons and 6 protons, and so that would have a net charge of 1 charge. The magnitude of that is the charge of the electron, but it would be positive instead of negative. Does that make sense?
Yeah, so it's the net charge?
Yeah.
All right.
Yeah, so just to clarify, let's see here. Ionized, so Q equals plus E. I mean, normally this would have 6 protons and 6 electrons, around it. And so what's happened is this is still, we haven't changed what element is. We've just changed the number of electrons. So when you add those together, that would be a net charge of plus E, i.e. the charge of a proton. Other questions on this guy? Okay, let's look at the second one. So I think our diagram, I don't know why this is moved. C is here. And sorry, was there another question? Okay, so let's look at this guy. So this is me trying to let you know that you need to be able to add vectors for magnetic fields as well. I know this appeared in the homework, but I hadn't quizzed or tested you on this. This is a fairly complicated skill, so if you have avoided the homework problems that ask you about this kind of thing, I suspect that you may find this quite challenging. Looking over people's results, it was definitely a spectrum. There were folks that got this completely right. There were also a lot of folks that didn't have this quite right. So I wanted to look at this one together. So like adding electric field vectors, it's kind of complicated because you need to find both the magnitude and the directions and then the components and add the components together. So the added issue with this is that unlike with, so if you had just a charge and you were, looking at the electric field is just radially away from the charge. So it's relatively easy to calculate like its angle, like if you need to know the angle. The magnetic field, though, is different because now if you have, a wire or something like we have here, the magnetic field is going in a circle around it. So in other words, it is the direction of B is perpendicular to R, the R vector. And so this adds a step and it makes keeping track of directions fairly complicated. The second or the third part of this question is the most difficult for sure. So when it comes to like an exam in person, I will give you, or an exam on this topic in particular, I'll give you something where the geometry is favorable so that you can compute it out and it will give you like a nice clean result. I'm not going to give you something where, it would be really complicated to calculate. So just be aware of that I have this in mind when I'm designing problems to test you on this skill. Okay, so if we're talking about a wire that's going into the page, like I just said, you know that the magnetic field is going to be in a circle around it. If I can even draw a circle, yikes. So that would be, into the page. Just do your right-hand rule, point your thumb into the current and wrap your fingers around, and that'll tell you the direction of the magnetic field. Now, for point C, this is fairly simple. So part B here, because you would have, let me actually label these I1 and I2. You would have a contribution from I1. And then you would also have a contribution from I2. If you imagine this as just being like part of a circle, right? They would both be pointing down. The one from I2 is going to be twice as large because it's closer. It's half the distance. So when you go to calculate this for B, you can tell, let me try and draw this slightly better here. Oh man. You can tell immediately that this will be in the negative J hat direction. It's in the negative Y. And you can also find the magnitude of this quite easily because you know that the B field due to a wire looks like mu naught I over 2 pi R. Well, the R is just going to be D and 2D respectively. So this becomes mu naught I over 2 pi D plus mu naught I over 2 pi 2D. And so if we were to draw this, the net field would be just these two added together. Maybe I can put that in a different color here. but it's, oh man, it's all in the same direction. And so when you add these together, you can see you would get, 3 halves mu naught I over 2 pi d. You have 1 half mu naught I over 2 pi d plus 2 halves. And so this would be, and then this would be in the, the negative, come on, pen. In the negative j hat. So this one is fairly simple because we didn't have to mess with any angles. All right. The second part is asking us about at point D. So this is a little more complicated because we have to take the angles into account. So it's similar in that we're going to have 2 contributions. And actually, it's simpler in a way in that the magnitudes are going to be the same because the R is the same. But we have to take into account the angles. So R from this point to this point would just be pointing like this. But if we think about the circle that would be, centered on I1, we know that B due to I1 would be pointing like this. And then R due to I2 would be pointing like this. And the B field due to that would be pointing, 90 degrees to it. So it would be sort of like this. And so just motivating this qualitatively, what we're looking for would be the sum of those 2 contributions. Because notice, this is B due to I2. Notice the X pieces are going to add together, while the Y pieces are going to cancel because they're symmetrical about the X direction. So, this, my picture doesn't really do it justice, but like this piece and this piece would cancel out and we would just be left with the X components. So basically what we need to do for this part is the net magnetic field is, well, I should say too, it's going to be, we can tell from our picture from working through this that this will be in the I hat direction. It's in the X direction. And so we need the magnitude times a factor of 2 because there's 2 contributions times this cosine theta. If you want to think of this angle here as theta. So let's work this out. Let's see here. Let me delete this. So the first thing, the magnitude. What's the magnitude going to be? Well, this would be mu naught I over 2 pi r. So we need r, in other words. R would be the square root of d over 2 squared plus d squared. So here's d over 2. It's going to be the hypotenuse of that triangle. One common thing I saw with people is you get turned around as to what these components are. Maybe you have d squared plus d squared, and that's not quite what you want. So this would be what we would want. And you could simplify this a little bit. This would be the same thing as root 5/4 d, or root 5 over 2 d. So when we go to find the magnitude then, for both of these contributions, it's just mu naught I over 2 pi times root 5/4 d. So notice this has the same units, which is one way you can check your work with these more complicated problems. This still is just, over a factor of length. We haven't changed anything. All we've done is picked up a numerical factor. So that's the B due to a current that far away. The other thing that we need is the direction. So let me actually try and redraw this here. And this is the part that got the most folks turned around. So we can talk about this in a couple different ways. Basically, we need to find this direction. We can easily enough calculate this angle. Let me call this one phi, say. And let's say that we're after actually theta. So phi d, this is d over 2. Tangent phi is going to equal d divided by d over 2. So in other words, phi is the arctangent of 2. You can see this would cancel and you get this would be equal to 2. So if you wanted to find this angle, you'd take the inverse tangent of 2, and that would tell you what that is. And that is, in degrees, it's about 63 degrees. So that would correspond to this angle here. So you need to add 90 degrees to that to get this direction to find theta. So in other words, theta would be negative 27 degrees. Okay. Now, when you do this exercise from the current at 2, it's going to look very similar. Now, here, let me do this in a different color. Now, R is pointing like this. This would become, this 63 degrees is over here. And so for this one, theta is positive 27 degrees. So it's symmetrical. My picture is breaking down here, but you get the idea. So, and this would be an acceptable enough way to express this. So we could add these pieces together. So the net magnetic field there would be both of those contributions. So, you know, the net field is going to be like this. So we would have 2, because there's 2 contributions, times this magnitude, mu naught I, 2 pi, root 5/4 d, times cosine of 27. So that would be an acceptable way to express this result. Another thing that you could do is you can express this angle in terms of d. So if you look at this, what it would amount to is basically, let's see, so we would need to find what this angle is in terms of d and other factors. So it would look like d over this radius, so which is actually root 5/4. And so we can re-express this cosine theta. It actually looks like the square root of 4/5. And so if you put that in for cosine, it will give you a little bit more concise result, because then this would become 2 mu naught I times root 4/5. And so you can see you would end up with something that looks like 2 mu naught I 2 pi d times 4/5. And, you know, you could further simplify this if you want, you know, lose this factor of 2 and stuff. But that, so then what would we have? We have 4 over 5 mu naught I over pi d. This would be sort of the most concise way. I don't necessarily expect you to have something like this when you're doing this kind of question in an exam environment. Something like this fully contains, you know, the result. This is just a little cleaner way to express it. So the things I noticed, I mean, looking over, folks get recognizing this 90 degrees issue. compared to like working with an electric field is definitely a complication and something that led a lot of folks astray. But there were folks that got this right too, so it indicates to me that at least some have messed with this in the homework, because there's been some homework that's more complicated than this question, where it's not as symmetrical and you have to use more complicated trigonometry and stuff. But this gives you a sense of kind of the level that you're expected to be able to do this kind of problem at. Oh, and I should say I left out the angle. This would be at, or the direction. This would be in the I direction. So something like this, or I hat, I would of course ask you to indicate the direction. Why go to all this effort to add these vector components if we're not going to be clear as to what direction it's going? Okay, so that's kind of a lot of me talking. Do you guys have questions about this problem? If you did not do the quiz, I would encourage you to do it and work through it and make sure that it's making sense. And for those that did it and ran into issues with your math and adding components and stuff, I would make sure that you're solid on this kind of question, because I'll definitely ask you something like this on the final. And I would add too, this might seem like kind of tedious. Why do we have to do a question that's this complicated? But I think it is perhaps not unlikely that you're not going to necessarily be doing lots of electromagnetic problems in the future, depending on what your major is, right? But this skill of being able to work with vectors, add components, break them down, be able to mess with geometry and trigonometry that's a little more complicated is a really good skill. It'll help you with other stuff, even that's stuff other than electromagnetic theory. So it's a good skill for you to be proficient at. Any questions at all? Are you alive? How about give me a thumbs up then if you want to move on. Also, if you have questions and you don't want to broach them, in this environment, but you got turned around on something on that, let me know. We can talk about it individually as well. Like I said, this is definitely a skill that you want to be proficient with for your final. So, all right, let's shift gears and talk about the last topic a little bit. Like I said, there is some video that's posted about this, so it's not. I'm not going to try and do a comprehensive discussion of this at this point, but we will try and connect things together a little bit, and I'll give you the big picture. Electromagnetic waves. So in some respects, this is kind of the culmination of the course. We've been doing all these, looking at different situations, talking about how charges cause electric fields and how currents cause magnetic fields and how changing magnetic flux induces an electric field. And the most recent thing that we had talked about was a couple corrections to our math. One was, this was kind of the last thing that we talked about last time, so I'll just recap. We made a modification to Ampere's law that accounted for the situation where, what if you have a situation where you don't have current, but you still have a magnetic field? And it was basically this discrepancy of imagining a parallel plate capacitor. And depending on how you define your Ampere's law surface, there either would be a current or there wouldn't be a current. So like if you define it like this, there is a current that's going through. But if you define the surface as this, there is no current that's going through. And this led to an additional term in Ampere's law. So, and you can think of it as sort of having the same behavior as a current, but it looks like a time-varying electric flux. So this was the last thing that we had added. And sometimes this is called the displacement current. that's sort of an outdated like way of referring to it, but the moral of the story with this is just that we had added this piece that makes for the more complete and correct Ampere's law. So another correction that we had to make, or not correction, is just one thing that we didn't talk about. It's in the video that's posted, but I'll mention it here too, is that you can do Gauss's law for magnetism as well. And it is simpler because there are no such thing as magnetic charges. So Gauss's law for magnetism is equal to 0. So this is another one of Maxwell's equations. So unlike for electric flux, remember E dot dA equals the charge enclosed over epsilon naught. For magnetic flux, this is equal to 0. And this is because you can think of this as being because that a magnet always has a north pole and a south pole. So no matter what surface you try and draw around this, you know, if you try and enclose this thing in a sphere or something, the magnetic field lines, you will always have as many magnetic field lines exiting that surface as you have entering that surface, no matter how you draw it. You can do it so that you cut through the magnet. So suppose this, you draw your surface and you're like, wow, I'm just going to get the north pole of the magnet. Not so, because there are field lines inside the magnet. If you were to break that magnet in half, you would see two magnets. You'd have both north and a south pole on each piece. And this is just an expression of the fact that there are no such thing as magnetic charges. You always have both. You sometimes hear this referred to as a monopoles either. Also, there's no charges or magnetic monopoles is another way of saying this. All right, so this at this point, this is everything we need to assemble Maxwell's equations. So I have this summarized online, but I'll do it quick here too, because it's just kind of like, this was sort of the result of the course in some ways. So we had Gauss's law. And we saw this way back this is one of the first things that we did back in chapter 22. When we just talked about the magnetic version of this. So this is this is Gauss's law for magnetism. And we just saw this in chapter 31. You see this in 31, section 2. And then what else did we have? Well, we had Faraday's law. A time-varying magnetic flux causes a voltage, causes an electric field. It was in chapter 29. And then the last one that we had just added this correction to, Ampere's law. So it looks like the line integral B dot dl looks like mu naught I, but also there's an additional term that's mu naught epsilon naught times the changing electric flux, the derivative of the electric flux. So this is sort of a summary of the course in some ways, the most important equations. And I'll tell you, actually, with your final and stuff, I'll provide Maxwell's equations to you. You don't have to remember or like use your study or your notes page for this. I'll provide these for you. So this is Maxwell's equations. How do we get electromagnetic waves out of this? Well, I'm going to skip one step that's sort of a derivation that you can see in the video, but I'll try and motivate it for you. If you look in vacuum, so think that you're in outer space or something, these equations will simplify. There would be no charge that's present, so E dot dA would also be 0, in addition to B dot dA. We would still have Faraday's law that a time-varying magnetic flux is going to cause an electric field. But now Ampere's law is going to be also simplified because there would be no current in vacuum. So think, outer space or whatever. And the thing that's kind of interesting to notice about this is that things look more symmetrical. So in this situation, in a vacuum, you don't have any electric or magnetic flux, or both Gauss's laws are equal to 0. They look the same. And also, we have two equations that look very similar. We have a changing magnetic flux is going to induce an electric field. A changing electric field is going to induce a magnetic field. So there's a sort of, they look sort of complementary. They look very similar, which is interesting. And basically, if you take this and you combine these together, you will find that you get a wave equation out. So the wave equation looks like this. You're not going to have to like derive this or anything. I just want to show you, and I want to ask you guys if you have seen a wave equation before in your math classes. So you can do this for the electric or the magnetic field. They're fundamentally related. And this is the differential equation that describes it. So what you'll see is you have an electric field, and perpendicular to that electric field, you will have a magnetic field. Oh man, it's going to be tough to draw. And, oh God. So if we were to look at this end on, they would be perpendicular to each other. And so you have two, separate fields. That are perpendicular to each other. And they travel in this direction. So in other words, V is in the direction of the cross product of E cross B. So the direction of propagation is perpendicular to both E and B, and E and B are perpendicular to each other. So let me ask you a question. So have you guys seen have you seen a wave equation before? The differential equation? Have you guys seen this? I guarantee you've seen the solution or something like it. So the solution for this looks like, well, there's different ways of writing it. You could write it as a sine, you could write it as a cosine, you could write it as an e to the j omega t or kx minus omega t. This could have a phase that's added to it. So it could look a lot of different ways. We'll just stick with this sine version just for simplicity of working with it. So have you seen this? No, no. I think so. I wouldn't necessarily expect you to have seen it, although I would think maybe like in differential equations or something you would run into this. It's okay if you haven't. I'm not going to ask you really to do anything with this. I just want to point out a couple things that are pretty cool about it, and then you'll do some simple problems with it, but not, or I should say, simple problems with the results of this, but not have to derive it or anything. So one thing that's really cool about this is that in this equation, this factor here is equal to v squared. So in other words, if you just have, any wave, like any wave equation, if this is whatever this is, this is the general form where this is a function of x and t. So this part in front is equal to v squared. So what that means is 1 over mu naught epsilon naught equals v squared. So if you want to find the speed of an electromagnetic wave, it equals 1 over the square root of mu naught times epsilon naught. So if you put your numbers in here, 4 pi times 10 to the minus 7 times, what was this, 8.85 times 10 to the minus 12, you will get out the speed of light, 3 times 10 to the 8th, which is pretty cool that the speed of light is predicted as a consequence of Maxwell's equations, as a consequence of looking at combining these constants that we've been working with for, we've encountered epsilon naught in the context of like parallel plate capacitor is probably where we used it the most. So and mu naught we talked about with regards to inductance a little bit. You put these ingredients together in the right way and you pull out the speed of light, which is cool. It also suggests that if you modify epsilon, like you put glass in your dielectric or in your capacitor, right? We remember how that changed epsilon. It made epsilon k times epsilon naught. In other words, if you make epsilon bigger, if you look at where that appears in terms of v, if you make epsilon bigger, the speed will go down. So that's why like the speed of light in glass is less. So another thing that pops out of this is that we can also express the speed as the wavelength times the frequency. So this is something that you'll be using in your homework if you haven't already done so. So for an electromagnetic wave, this is equal to c. So if you know the wavelength or the frequency, you can figure out, because you know the speed of light, what the other would be. So for example, you can figure out the wavelength for like a radio station. This will be the last thing that we'll look at. Like when I was coming to school today, let's see, public radio I think is 89.7. So that is 89.7 megahertz. We know what the speed of light is, so we can find what lambda would be. It's 3 times 10 to the 8th speed of light divided by 89.7 times 10 to the 6th per second, right, hertz. And so we can compute what that is. I don't actually have the number in front of me, but we can divide it quick here and figure out what it is. So this would have a wavelength of 3.3 meters. So you'll be asked to do stuff like that in your homework. Given a frequency or given a wavelength, you can find out the unknown quantity using this connection that just the speed is equal to the wavelength times the frequency. So this is one of the things that you're responsible for that's based on this electromagnetic waves. Getting familiar with how to work with the solution. It's one of the simple relationships that falls out of this. I'll probably post a little bit more stuff about this, maybe some additional examples or something, but this is most all of what you're responsible for the course. So there's maybe one or two small topics yet, but that's all we have time for today. I hope that you see that as being kind of interesting, that you can pull the speed of light out of the constants that we've been working on for these very different, purposes. Do you guys have questions?
I'm all good.
All right, I'm going to stop the recording. If you have additional questions, feel free to stick around.